Hello. So good morning. My name is Abhishek Kirar, and a warm greeting from my side to Alma Beta team. So in this video, I am going to talk about some more topics regarding machine learning. So in this video, I am going to cover few of the topics as I covered in the first video. So after that, I also want to cover some more topics. So with a brief idea about the concept, not in much detail, but I want to share my experience. So first, we are going to see that in machine learning, we, we generally hear about the hyperparameters and what is that, what is hyperparameter, and what we also do some hyperparameter tuning. So hyperparameters are basically those are given by a practitioner for achieving the optimum result or to improve the model accuracy. So hype and so we can take some example that hyperparameters are like the in if we talk about the gradient descent algorithm. So the learning rate is basically a hyperparameter for that algorithm. Also, if we talk about the number of trees in random forest, so that number of trees are basically hyperparameters, and also the regularization coefficient in linear or logistic regression, and also the number of clusters in k-mean clustering algorithm. So the number of clusters is basically hyperparameter. So and if we talk about the hyperparameter tuning, so it is just called as hyperparameter optimization. So it is a process of systematically searching the best combination of different hyperparameters for a given model and data set, and this can be done by training the model applying different hyperparameter setting. So basically hyperparameters are the tuning knobs or switches to adjust the machine learning model for work better. So now we come to the that how would you evaluate an unsupervised learning project. So evaluating the unsupervised learning is quite challenging than supervised learning because you don't have the clear performance metrics to evaluate the model. So here are some ways to evaluate the unsupervised model. So the most common way to evaluate to compare these clusters to external measures of ground truth. And another way is to use metrics like Jaccard similarity, adjusted Rand index, normalized mutual information. And these metrics compare the predicted clusters and provide scores that ranges from 0 to 1, and that refers to perfect match. And another way to use Silhouette score, which computes the similarity of each data points and to its own cluster and compares with other clusters, and its value ranges from -1 to 1. And also we can visually inspect the clusters. And no, last but not the least, that there is also a method called twin sample validation. So now if we move to the that if we move the classification threshold to from 0.3 to 0.5, then what will be the precision recall? It will it be increase or decrease, and why it would so? So if we move the classification threshold from 0.3 to 0.5, the precision and will increase and recall will decrease. So let's look why this happens. So precision is the ratio of true positive to all the positive prediction done by our model, and recall is the ratio of true positive and true positive to the true positive and false negative. So in simple terms, precision is a measure of how many of the items that the model classified as positives are actually positive, while recall is a measure of how many of the true positive examples the model is able to identify. So when the threshold is set to 0.5, then the model is more relaxed in classifying example as positive, so which will increase recall. So since more true positive example will be included, but decrease precision since more false positive examples will be included. So when the threshold is increased to 0.5, the model becomes more strict in classifying examples as positive, which will decrease recall. And since fewer true positive example will be included, so that's that's referred to increase in precision. So since fewer false positive example will be included. Now, if we go to the term called what is test set and validation set, and what basically what we are going to see what are the difference between these sets, and also why validation set is required. So basically, test set is a set of data which is used for evaluating the model performance after it being trained. So it is also used for checking how our model will perform against unseen data. So usually, as compared to training and validation, it has very less proportion, maybe 20 to 10%. And if we talk about the validation set, so it is also a set of data that is used to tune the hyperparameters of the model, and that are set before training. So validation set is used to evaluate the model performance while tuning the hyperparameters. And also validation set is used during the model selection and hyperparameter tuning process. So for preserving the test set, which is unseen to trained model, if we expose the test data to our model while train this, can lead to overfitting and poor generalization to new unseen data. So now we are going to see that how to find the right threshold for classification problem. So now finding the right threshold for classification problem, it basically depends on specific problem statement and desired outcome. So there are various methods for determining the right threshold for a classification model. So uh, we not going in much detail about the topics, but there are different methods. Is called some, first is manual tuning, and the second one is ROC based method, and the third is in Bayesian optimization, and the last one is metric based approach. So these are the different kinds of approach for finding the right threshold for classification problems. So now we are going to see some regularization techniques in brief. So regularization is used for is just to prevent overfitting by reducing the variance and the variance of the machine learning model, we can say. So it can be implemented by modifying the loss function and also sampling method, uh, or training the model approach. So there are some common approaches of regularization. First one is lasso regularization. So it is also known as L1 regularization. So it is the technique for reducing the variance by adding the penalty term to the loss function, and the penalty term in lasso regression is basically modulus form, and which is not differentiable at global minima, and it also used for feature selection when the data set is too large. So yeah. And we talk about the other regularization technique, which is called as ridge normalization, or we can say L2 regularization. So it is a method of estimating the coefficient of multiple regression models. So in scenarios where the independent variables are highly correlated. So these were some common techniques for regularization. So now we are going to see what is bagging and boosting in machine learning. So bagging is basically is an it is an ensemble technique that is commonly used for reducing the overfitting in data set by randomly sampling small subsample of the data set, and it is also called as or known as bootstrap aggregation. So it resample sample of the data with a replacement, and so that is there is might be a chance of repetition of rows and columns in data set. And so, and if we talk about the boosting technique, so it in boosting we choose random some sample from data set and train it sequentially, and each model compensate weakness of its previous model, and with the help of many weak learner, we obtain a strong learner. So basically the further model is trained on previous models error. So this is about boosting and bagging. Now, if we talk about what are the difference between Euclidean distance and Manhattan distance. So basically, Euclidean distance and Manhattan distance both are used to calculate the distance between the 2 points in multi-dimensional space or place, and but their approaches are different. So in Euclidean distance, it is the ordinary distance between 2 points in Euclidean space, also known as a straight line, uh, or we can take example of two-dimensional space. So the Euclidean distance between 2 point x1 y1 and x2 y2 will be the square root of x1 minus x2 whole square plus y1 minus y2 whole square. And if we talk about the Manhattan distance, so basically Manhattan distance is also known as L1 distance or taxi cab. So, and it is calculated by sum of the absolute difference between two coordinates, point in dimension, two-dimensional space. So, we can say the Manhattan distance between 2 points x1, y1 and x2, y2. So, it is basically the modulus of uh, x1 minus x2 plus y1 minus y2. So, if we move forward, we will see that what is the functioning of KNN algorithm and why is it referred to as a lazy learner. So K nearest neighbor, or known as KNN algorithm, it is a simple yet powerful algorithm for classification and regression problems. So the basic idea behind KNN is to find the K data points in the training set that are closest to a given test point, and then to predict the level of the test point based on the levels of its K nearest neighbors. So how KNN works. So the KNN algorithm starts by taking a training data set of level data points, and each data point in the data set training set is a vector of features, and it is an associate label. And if we talk about, and we'll say when a new test point is encountered, so the KNN algorithm finds the K training points that are closest to the test point based on some distance metric such as Euclidean or Manhattan distance. And the third point is the level of the test point is then predicted by majority voting of the K nearest neighbors. So in other words, the label that appears most frequently among the K nearest neighbors is assigned to the test points. And also the last point is the value of K is usually chosen by the user, and it can be any positive integer, and a default value is set to K is equal to 5. And but the optimal value of K depends on the specific problem and data set. So we can conclude that the KNN algorithm, and not conclude, we can say why it is called lazy learner. So it does not do any work until it asks to make a prediction. So it simply stores the training data, and when a new data point is encountered, it finds the K nearest neighbors in the training data and makes a prediction based on their labels. So this is all about KNN algorithm. So now if we move forward, then there is a question that what do you mean by model explainability, and how would you introduce explainability to a black box model? So basically, model explainability is referred to the ability to understand and interpret the decision made by the model. And introducing the model explainability to black box model is important because in some cases like deep neural network, so in basically in deep neural networks, the practitioner wants to know why this kind of prediction was made and how much to trust the prediction. So there are several ways to introduce the explainability to black box model. So first is feature importance, and the second one is local interpretation. Third one is model visualization. Fourth one is post hoc methods, and the last one is saliency map. So this is not always suitable while trading between explainability and model accuracy. So it is not always possible to make model explainable. So sometimes we just take predictions and work on that. Not every time we just want to know the logic or the whole calculation behind the models working. So now there is a question that how do you evaluate a regression problem and what is the difference between R2 and adjusted R2? So for evaluating the regression model, we have various performance ma matrices. So first is MSE, then which is basically mean squared error, and other one is MEA, which is mean absolute error. Other one is RMSE, then R square or R2 score, and the last one is adjusted R square score. So MSE, ME, and MSE used for determine the errors in model, and R2 score and adjusted R2 score used for determining the variance explained by our model. It basically tells how accurate our model is. So the main difference between R2 and our adjusted R2 score is basically it takes feature into consideration. So whether it is important or not, however, R2 score always increases when you add up a new feature into dataset. So now we'll say that what are the difference between deep learning and machine learning. So machine learning and deep learning, they both are related to artificial intelligence. So where deep learning is a subset of machine learning, so with more complex structure and computational power. So however, some key differences we will see. So first difference is based on the architecture. So deep learning are based on deep neural networks and which contains huge number of hidden layers in them, and machine learning is based on statistical models or solo architecture, so such as decision trees or linear regression. And if we talk about the computation, so deep learning requires large computational power as compared to the ML models. And in terms of tasks, so deep learning is used for image classification, speech recognition, and NLP. And also if we talk about the machine learning, so it is used for prediction, clustering, and classification. And it has wider range of application, and it's not limited to perception tasks. So now if we talk about in terms of scale of the data, so deep learning models are able to learn from huge amounts of data, whereas traditional machine learning models may struggle to learn from a large set of data set. So now if we differentiate these two in terms of representation, so deep learning models can automatically learn features from raw data and learn complex nonlinear relationships between inputs and outputs. So traditional machine learning models, on the other hand, rely on the practitioner to provide a set of features or representation of the data, so which can be a labor intensive and error prone process. So this is basically the difference between the deep learning and machine learning. So now if we move forward, so then we will see that what is the difference between gradient boosting and ADA boosting. So gradient boosting and ADA boost both are ensemble learning techniques, which means they combine multiple models output for predictions and provide better result, and they are used for classification and regression problems or regression tasks. So there are some key difference between these two. So if we talk about the gradient boosting, so it iteratively trains the weak models such as decision trees and combines them to make powerful ensemble model. So uh, so the training data set it trained the data set so that the data were predicted wrong by previous models have a higher weight. So now if we talk about the ADA boost, so it also iteratively trains the weak model and combines them to make the powerful ensemble model. So instead of adjusting weight of training data, so it adjusts the weight of models in the ensemble group. So it gives more weight to the model who is more accurate, similarly raised to having less accuracy. So this ensemble is in more accurate overall. So uh, we can say that the gradient boost model, gradient boosting is more powerful than ADA boost. So, and it is also more sensitive to overfitting, and it requires more tuning. That's why we give preference to gradient boosting over the ADA boost. So now, if we move forward, then we will see what is vanishing and exploding gradient. So uh, we can say that vanishing gradient and exploding gradient usually occurs while training the deep neural network. So when the derivative of the activation function extremely small or becomes zero. So this phenomena is called a vanishing gradient problem. And there are more layers in the network. So the value of the product of derivative decreases until at some point the partial derivative of the loss function approaches value close to zero and the partial derivative vanishes. So now if we talk about the exploding gradient problem, so it is inverse of vanishing gradient. So when a large error accumulate, resulting in extremely large update in neural network model. So model weight. So during training, as the model is unstable and fails to learn the data. So this is a brief about the vanishing gradient and exploding gradient. Now we come to know about that what is the difference between ANN and CNN and why CNN is used for image processing. So NN is basically the abbreviation of artificial neural network, and similarly CNN is abbreviation of convolutional neural network. So both are built on the base of neural networks, but the application of these two are different. So one is used for solving complex problems, and other is used for solving computer vision related problems. So ANN is a type of machine learning model that is inspired by the structure and the function of human brain. So it consists of a large number of interconnected artificial neurons that process information by propagating signals from input to output. And ANN can be used for a wide range of tasks, including pattern recognition, time series forecasting, and natural language processing. So on the other hand, convolutional neural networks is a specific type of ANN or artificial neural network. So it is designed to process data with a grid-like topology and such as an image. So in CNN, the layers of artificial neurons are arranged in 3 dimensions. So width, height, and depth. So each neuron in the first layer of the networks is connected to a small region of the input image rather than the entire image. So this allows the network to learn a set of filters that can detect specific features in the input such as edges or texture. So this is all for the day. So we basically uh, went through some 15 numbers of questions, and we just take a brief on the topic, not went to much detail. So if the time permits and the future permits, we will see these topics in more detail and in, or we can say, in more connection with the real world problem. So this is all about the day. So thank you very much. Thank you, Alma Beta team.